geometric sequences. So geometric sequences are very similar to arithmetic. So remember there's three different types. Arithmetic goes into linear, geometric actually goes into exponential, and that's exactly our definition of a geometric sequence. So our geometric, because we have an exponential, we have a common ratio now, where it's a division. So it's the second number divided by the first number. That's going to be our R value itself. And our equation is this, again, an exponential function. So it scales up just like an exponential, this way, this way. Okay. So how we do this? Very simple. First, we got to find a common ratio. It's always second term divided by our first term. So our common ratio is going to be 3 this time. So our equation is going to be a sub n is equal to a1, which is 2, times 3 to the n minus 1. Now that makes sense, right? So if n is 1, this becomes 0, so 3 to 0 is 1, times 2 is 2. If n is 2, 2 minus 1 is 1, 3 to the 1 power is 3, times 2, 6. So it does actually work to be an exponential. Okay, so we'll just keep going from here. So next one is, again, common ratio. Just remember it's always this times that, just like the subtraction. Second minus the first, so 9 over 10. So it can be simplified, so literally that's all it is. So our equation is going to be a sub n equals to 10 times, and this I'll put in parentheses, like that. Okay. All right, so again, now that we have our equation, we can do the same thing as all the other sequences. Now we can find some term given that. So we did this earlier. This is the same equation as the last example. Now we want to find the 54th term. So this one, however, you're probably going to put in decimal. You probably don't want it in fraction because it's going to be a huge number, right? So again, you plug in 54 in for n. And again, because it's exponential, it's going to drastically get much, much larger itself. Okay? And in most cases, when you do a ratio, or actually find a ratio, you usually put this in decimal format. So in most cases, you would see it like this as growth and decay exponential models. So you get about that. Which makes sense, right? It's 0.9 to something that's not even 1, so it's going to get even smaller. On the contrary, something just grows in exponentially. So 14 over 7 is going to give you 2. So common ratio is 2, so a sub n is equal to 7, 2 to the negative 1 power, or n minus 1 power. Again, finding the 54th term. So 7 times 2 to the 54 minus 1, right? So it gets drastically bigger as we go along. And in most times, the calculator can't even do it. It would probably give you the scientific notation. So you get something very, very big. It's like this. It's huge. Huge number. That's why in most cases, these are done for smaller numbers. Things like just drag those smaller this way instead of this way. And the last thing is the sum, right? We can find the sum of the first few terms of a geometric sequence given to be this. Now, this equation isn't as fun to look at as itself, but, you know, it's not that difficult. It all depends on your first term and the common ratio. That's pretty much all you really need. Okay? But again, you have to identify what the common ratio would be in this case using our equation itself. So first off, just plug in 1 in for n, so it'll be just 1/2. Or again, if you want in decimal form, 0.5. And now we also need the term we want to stop at. In this case, it's going to be 42. So a sub 42 would again just be plugging in 42 here. But we have a bit of a problem. Oh, we'll just go from there. So, not yet, we'll just say. So this is basically 0. If you just 1/2 to the 42 power, it's basically 0. But one of the most important things going forward is identifying this r. Okay. Now, according to our equation, it must look like this, where the common ratio is right here, right there. This time, however, because there's an n, you have to manipulate this using exponential rules. So I can rewrite this to look like this. Now, why does this work? I'm glad it's a great question. So let's go back to what exponential rules mean. So if I have x times x raised to the n, for instance, well, that means I'm just adding the powers together. So this would be x raised to the n plus 1 power. So these two combined give you this. If I split it up, it gives me this part here. And that's what I did here. So I would split up x to the n to be x to the first times x to the n minus 1. Because what happens when I add them together? The ones cancel, and I just get n itself back. Okay. So now you know that the r is actually 1/2. So just very deceptive, just in case of that kind of part there. So to find this sum, to finish up this problem, is going to be 1/2 times 1 minus 1/2 to the 42 power, which is basically going to be 0, over 1 minus 1/2. And then we just simplify that portion going forward. So these are going to be really, really small numbers or really, really big numbers, depending on what we want. Again, all you have to really care about is defining what the r value is. And sometimes they give it to you right here. So for instance, right, we just plug in, so the r value is going to be 2/3 because it's already in that format. So this is our r value. And our a sub 1 is just plug in 1, we just get 2. Same thing here, we're just manipulating this portion because this is the slope that we want it. This is, again, the same thing as writing it 1/4 times 2 raised to the n minus 1 power. So our a sub 1 would just be 1/4, and our r value would be 2 in this case. And then just plug it in to get the sum of the series.